Hello everyone, welcome back to EMA 3413. This is lecture 26, a makeup lecture for March the 19th. In this lecture, we'll try to finish up the chapter on semiconductor devices, and we'll talk about p-n junctions, looking at its characteristics under bias, and then we'll also talk about field effect transistors. First of all, let's look at p-n junctions. Okay, last lecture we have talked about the behavior of the p-n junctions under thermal equilibrium. We have to have a constant Fermi energy throughout, so we have to have band bending both on the p side and on the n side of this junction to achieve this constant Fermi energy. We're going to have a depletion region somewhere in the middle because with the free carriers will move around as a result of the Fermi level being away from the conduction or valence band edges. This is going to be different from either side of the bulk. This building potential is important in this p-n junction. We talk about how to calculate the building potential across the two sides given the doping concentrations of the N and P side. Now, let's also look at the forward bias situation. This is very similar to the metal semiconductor contact. The forward bias is going to be applied to reduce the total amount of band bending. So in this case, the P side of the p-n junction will be connected to the positive bias, and the N side will be connected to the negative terminal of the voltage supply. So in this case, if you apply half a volt here, the band bending will be reduced by half an electron volts. Okay, so in this case, the N side will have a higher Fermi energy than the P side, just because the potential that we apply here. The total band bending, as I mentioned, will be reduced under this forward bias condition. And to remember the polarity, remember the P side connects to the positive, N side connects to the negative end of these voltage supply. We can also apply a reverse bias by just simply reversing the polarity of the voltage supply on the semiconductor p-n junction we apply. So in this case, the P side connects to the negative end, and N side connects to the positive end of the voltage supply. So in this case, this is similar to the metal semiconductor contact case. The building potential will be in the same direction as a reverse bias voltage, so that overall the total band bending will be increased. So if you want to sum up the two sides, if you just say, okay, we apply a voltage bias and then following the convention here, then the voltage is positive, means that we have a forward bias, and then the reverse bias, obviously the voltage is negative. Now also note that the depletion region width does depend on the total amount of band bending. So obviously in this case, if we do have a forward bias, we reduce the total band bending, then correspondingly the depletion region will be slightly reduced, and square root dependence on it. If we apply a reverse bias, we will increase the total amount of band bending, and as a result, we will increase the depletion region width as well. So now, we have this band diagrams under forward or reverse bias, but eventually we want to know, under these bias situations, how does the current actually behave differently with these two different situations, and how does the current depend on the voltage overall? So let's look at the forward bias situation. As I mentioned, the N side will have slightly higher Fermi energy or chemical potential than the chemical potential on the other side. Okay, so in this case, the electron, the reduced band bending will allow the electrons to basically flow through onto the other side. But obviously, as electrons flow into the P side, they become minority carriers. But because of the higher Fermi energy on the N side and the P side, that carrier concentration of electrons at the edge of the depletion region will be significantly higher than it was previously. So this means that looking at this profile of carrier concentration, so this is electron concentration on this N side, and we have an significantly increased electron concentration just outside the depletion region width of the P side. So this amount increase really is basically the voltage, relates to the voltage that you apply. So if you apply a positive voltage forward bias, then this electron concentration, remember this, we're looking at the electron concentration right at the edge of the depletion region, okay, on the P side. Okay, so these are the minority carriers. So that means that we're going to have an exponentially increasing minority carrier concentration on both sides, and that exponential increase is related to the voltage we apply. So on the forward bias, we have excess carriers, and on the reverse bias, we have basically a deficiency. So the baseline that are shown here are the electron concentrations in the p side and the hole concentration on the n side. So these are the minority carriers. Okay. So this is the forward bias situation. We have electron concentration starting at a certain level. This is dictated by the doping concentration in the n-type semiconductor. And then there will be a little increase, which we can neglect at this point. But the important thing is that these electrons can actually flow through to the other side because of the reduced band bending, so that we will obtain a significantly higher minority carrier concentration on the opposite side. So now, with the high concentration of minority carriers, as they move further across, they will be recombined with the massive amount of holes we have in the p side. So that means that as we move further away from the depletion region, we are going to be seeing a significant decrease in the excess minority carriers, and eventually it'll get back to normal. And this is a process of having, because these excess electrons will be diffusing into the neutral region of the p-type semiconductor. So this is what we call a diffusion current. And obviously on the other side, the n side, we are also going to have these excess holes diffusing into the neutral n-type semiconductor, causing a diffusion current. So if you look at the current, we have a diffusion current for the electrons, the minority carriers in the p side, and we have a diffusion current for the holes, the minority carriers on the n side. That diffusion current will gradually die down just because we are dissipating all those excess carriers right outside the depletion region. Now, in the ideal diode situation, we assume that the carrier recombination inside the depletion region or the space charge region is negligible. So that's why we maintain a constant electron current or the whole current inside the space charge region or the depletion region. But on the other side, obviously, if you need to supply all those electrons to the other side, you have to flow these electrons through the neutral region. That's why there's a slight increase of carrier concentration at the interface, because we have a slight increase of carrier concentration for the minority carriers. So the majority carrier will increase as well. But overall, you have a continuity of the electron movement across. But overall, when you sum up the total current of electron holes, it has to be constant because you have to maintain the current continuity. Okay, so the way to obtain the total current is just to look at the currents that we have for the electrons and the holes on the opposite side. When they become minority carriers, they are diffusing in. So when we look at the edge of the depletion region, by looking at these two currents, when we add them up, we can get to the total current. Okay, so without going into all those details, this is going to be the diffusion current for holes in the inside, right at the edge of the space charge region. There's going to be having a factor e to the qv over kt minus 1. Remember, this is the same factor that we have seen in the Shockley diode equation for the metals for a Schottky contact. Okay, and then there are a few other terms in front of that. Q is the charge, D is the diffusion coefficient of holes in the n-type semiconductor. So remember, holes are the minority carriers in the n-type semiconductor. And then Pn0, that's the hole concentration on the n side under thermal equilibrium. So that's what these labels are. P means hole concentration. The subscript n means it's on the n side, and 0 means that it's under thermal equilibrium. So that basically that's very, very far away from the interface, from the metallurgical junction. And here underneath, we have L sub P. That's the so-called diffusion length of these minority carriers. Okay, so basically it shows you how far these holes can, the excess hole concentration can last into the neutral region of this n-type semiconductor. So this is the hole current at the Schottky, at the space charge region edge. But you can also get a similar equation for the electron current on the other side of the space charge region. And then when you add these two things together, you get to the total current. So this is what's shown here. you have these two components, the whole current and the electron current. You add them up to the total current. So basically, you have the same voltage dependence on both sides, but the prefactors are different. So when you put together total, the two terms for the prefactor, you have this reverse bias saturation current density. And inside, it's the same thing as we have seen earlier. So this is the Shockley diode equation. And we call it ideal diode equation because we're making some assumptions for the characteristics of this diode to achieve this ideal diode characteristics. Okay, so this is, as we talked about earlier, when we look at the Schottky diodes, this is so-called a rectifying junction. Current basically can only flow in one direction under the forward bias situation. On the reverse bias, it very quickly saturates to this reverse bias saturation current density. This is the IV characteristics, current voltage characteristics in the sort of linear plot. You can, if you look at the semi-log plot of the current as a function of voltage, you see the forward current. Basically, as soon as the voltage goes above a few kT, then you can see basically an exponential increasing current. This is log scale, this is linear, so that's why you see a straight line for the exponential increase. On the reverse bias, it very quickly saturates to a relatively low level. And you see that at some significant voltages, the forward and reverse bias can be very, very different. And we call this so-called rectification ratio. Basically, at the same voltage, in this case, let's say if you look at 10 kT, that's actually only, for voltage-wise, this is only 0.26 volt. 0.26 volt forward bias versus 0.26 volt reverse bias. You see that the rectification ratio will be 1, 2, 3, roughly about 4 orders of magnitude, 10 to the 4th. And it could be even bigger than that if you go to even higher voltage. So that shows you that really you only need to care about the current transport in the forward bias situation. On the reverse bias, essentially this diode is shut down. So now this diode, obviously this is going to be one of the very, very significant, very, very important building blocks for modern electronics. It gives you a rectifying behavior so that it has opportunity to convert AC to DC currents. But it goes much more beyond that. And there are many, many other more complicated devices that use these diodes as basic building blocks. But diodes, basically, we talk about two kinds, PN junctions and Schottky junctions, and these are so-called two-terminal devices. You have a positive terminal, you have a negative terminal, and across these two terminals, you apply a voltage. Sometimes you apply forward bias, sometimes you apply a reverse bias, depending on the situations. And so the current can flow through these two terminals, and then obviously the current, it can be varied by the voltage bias that you apply across the two terminals. Sometimes the current will be negligible under the reverse bias situation. Sometimes this current can increase exponentially with the voltage that's under the forward bias situation. Okay, that's what we talk about, the so-called rectifying behavior. But there are sometimes devices with 3 or more terminals. And an example is so-called transistors. So you still have current flowing between two terminals, but that current flow, well, it'll still depend on the voltage you apply between these two terminals. But at the same time, that current can be modulated or so-called gated by a third terminal. We call it gate electrode. So just like think about, you have a pipe, water is running through the pipe, and you have a valve on top. When you close the valve, you turn off the flow, even though you may have water pressure across the two ends of the pipe, like you get the water from the faucet. Okay, the power supply, the water supply from the water company, they have a positive pressure, and then it can flow if you open the valve. But when you close the valve, the flow is cut off. Okay, so that gating effect is important in these transistors, and one of the possibilities to achieve this gating effect is use so-called field effect. Okay, so this is what we're going to talk about next, the field effect transistors. And one of the main kind is so-called MOSFET, metal oxide semiconductor field effect transistors, and MOSFET. Sometimes people call it MISFET. They use the word insulator instead of oxide. There are other kind of transistors. simply metal semiconductor field effect transistor using the Schottky contact between the metal and semiconductor. You can also achieve the field effect behavior. And there are other kind of transistors like the bipolar transistor. This is more important for these analog electronics. The field effect transistors are more important for these digital electronics, which is what we are using in computer chips these days. So let's look at this MOS or MIS structure. Okay, simply it's metal on top of a oxide or other kind of insulator on top of a semiconductor, and we use MOS because very often we are using silicon to make these electronic devices, and then naturally we can, if we can grow high quality oxide layer on the silicon surface, and then you have, once you deposit metal on the other side, you have this very simple MOS, metal oxide semiconductor structure. The heart of the MOSFETs is this MOS structure. So we need to understand how this gating effect actually works. Okay, and then you can look at this Venn diagram under the ideal situation. You have metal having sort of work function, vacuum level here, and then the oxide. In this case, let's not worry about where the conduction band edge is. Just assume that the conduction band is high enough, and then we can really move carriers across this oxide layer. It's an insulator. On the semiconductor side, we have conduction band edge, valence band edge, some Fermi level, and then obviously you have seen the definition of the electron affinity and work function and so on. Important thing to understand here is that under this ideal situation, there's no current flowing through the oxide, so there's no direct current between the metal and the semiconductor. They are isolated by the oxide in the middle. But you can apply electric field. Okay, if you do apply electric field, this electric field can actually influence the carrier distribution inside the semiconductor. And very specifically, it can cause carriers to move, basically attract carriers to the interface or push carriers away, depending on what kind of voltage you apply on the gate electrode. Okay, so like in this situation, we can have so-called accumulation. If you have a p-type semiconductor, p-type semiconductor means that the Fermi level is going to be below the intrinsic Fermi level. The Fermi level is in the lower half of the band gap. Okay, now in this case, the majority carriers are the holes, minority carriers are the electrons. So in this case, if we apply a negative voltage on the gate bias, this negative voltage with respect to the semiconductor, let's say the semiconductor bulk is grounded. When you apply a negative bias on this metal, that negative bias is going to attract some of the holes to the surface of the semiconductor. Remember this negative bias. So the electric field points from the semiconductor through the oxide into the metal, and that means that we can actually push some of these holes. Holes carry positive charge. So naturally, you can think about the positive charge are attracted by the negative potential that you apply on the metal. But these holes cannot move across the oxide because for the oxide, it has a very wide band gap. So the conduction band edge and valence band edge are going to be beyond the reach of the conduction band and valence band edges of the semiconductor. So the holes will actually be stopped at this interface. So if you have holes, a lot of holes coming in, but they cannot move across, naturally you're going to have a higher hole concentration at the surface of the semiconductor than in the bulk of the semiconductor. Now, if it's an N-type semiconductor, then we have the Fermi level being in the upper half of the band gap above the intrinsic Fermi level. Majority carriers are the electrons. So in that case, if you apply a positive bias on the metal with respect to the bulk of the semiconductor, then the positive voltage is going to attract the electrons to the surface of the semiconductor. But again, electrons cannot move across the oxide. They're going to be stopped by the oxide layer. That means they will be accumulating at the surface of the semiconductor. So we're going to have a higher concentration of electrons, the majority carriers, at the surface of the semiconductor than in the bulk. This is what we so-called the accumulation region. If you have accumulation, naturally you can have depletion. Okay, depletion means that you are pushing carriers, the majority carriers, away from the surface. So in the case of p-type semiconductor, if you want to push the holes, the positive charges away from the surface, you have to apply a positive voltage so that you have the electric field pointing from the metal toward the semiconductor so that you can push the holes away. That's so-called depletion region. In the case of N-type semiconductor, you just need to apply a negative bias to push the negative electrons away from the surface. So in both cases, the majority carrier concentration at the surface is less than the majority carrier concentration in the bulk. That's what we call a depletion region. Well, if you push them too hard, well, like in the case of P-type semiconductor, you may be pushing too many holes away such that the bands are bended so that the Fermi level at the surface actually move across. They will have a crossover with intrinsic Fermi level. Okay, remember, the difference between the Fermi level and the band edges dictates, very strongly related to the carrier concentration. So if you are pushing too many holes away, at the same time, you may be attracting some electrons to the surface. So essentially, when you have a band bending like this, the band bending is so strong such that the Fermi level crosses over from the intrinsic Fermi level near the surface region. Like in the case of P-type semiconductor, in the bulk, it's in the lower half of the band gap. But at the surface, it could be in the upper half of the band gap if you apply a very large form of positive bias. In the case of an N-type semiconductor, again, you apply a negative bias. If the negative bias is so large such that in addition to pushing the holes, electrons away, it's also attracting holes to the surface, such that now in the surface region, you're going to have more holes than electrons. That means the Fermi level will be in the lower half instead of being in the upper half of this N-type semiconductor. So this is what we call inversion. That means in the bulk, like P-type semiconductor, you have more holes than electrons, but at the surface, you're going to have more electrons than holes. It's inverted. So like the bulk is P-type, but the surface is really, you can call it an N-type surface. In the case of N-type semiconductor, bulk is N-type, but the surface is P-type. You have more holes than electrons. You have an inverted situation. This is when this positive voltage or reverse of the negative voltage is really, really high. But there's also a small difference between this inversion. We call it weak inversion versus strong inversion. Weak inversion means that at the surface, the requirement is that you only need to invert the surface type from the bulk. So like in this case, we're showing a P-type semiconductor. Fermi level is in the lower half of the band gap. So this is a P-type semiconductor. So the weak inversion only requires that the surface becomes N-type. So the electron concentration at the surface is 0 here. That's the axis here. We start from the surface, the interface between the oxide and the semiconductor. So that's the surface of the semiconductor. We call that x equals 0, and then we go deep into the semiconductor. So this 0 means that we're at the surface of the semiconductor. So weak inversion only means that we have more electrons than holes at the surface of this P-type semiconductor. This is weak inversion, and that if you look at the Fermi level as a function of, with respect to the intrinsic Fermi level, in the bulk, Fermi level is below the intrinsic Fermi level. That's the characteristics of a P-type semiconductor. For N-type, the Fermi level crosses over to be in the upper half of the band gap, so it's above the intrinsic Fermi level. That's inversion. Okay, so weak inversion means that as soon as it crosses over, now you get to the weak inversion process. But you can also look at how much the band is bended. Remember, Fermi level is constant, so how much the bands are bended really dictates whether the intrinsic Fermi level can cross over to the Fermi level. Okay, so if you define the so-called surface potential is really looking at how much the bands bended. Okay, the potential at the surface with respect to the bulk. Okay, so so there is a range for the surface potential to achieve this weak inversion. But now, if the band bending is so much such that the electron concentration at the surface not only is greater than the whole concentration at the surface, it's actually greater than the whole concentration in the bulk. So that's what we call a strong inversion. So basically, if let's say the Fermi level is at about 0.2 eV above vacuum level, above the valence band edge, then at the surface, the Fermi level needs to be closer to the conduction band edge by that amount. So this difference, energy difference, meets this energy difference. That's when we get to strong inversion. I mean, we are assuming that the effective density of states is roughly the same in the conduction of valence band edge. So basically, when you have the Fermi level being closer to the conduction band edge than it is to the valence band edge in the bulk, then we run into the so-called strong inversion, and we get to more electrons at the surface, higher concentration of electrons at the surface than whole concentration in the bulk. And this is what we call a strong inversion. And this is really the region where we use to create this field effect transistor. So if you look at the device structure of the field effect transistor, we have a MOS structure in the middle, metal, oxide, and semiconductor. So we are using the p-type semiconductor as the example. So the substrate is a p-type semiconductor. And then at the same time, we have two additional electrodes. This is the metal electrode in the middle, we call it gate electrode. But also we need to create a conducting channel. There's no current flowing across the oxide. So the conducting channel is really underneath the oxide at the surface of the semiconductor. So to make contact with this surface channel, we need to have two more electrodes. We call it source and drain. These are the electrodes sort of laying down side by side on either side of the gate electrode, and then underneath the source and drain region, we'll dope the semiconductor very, very heavily into N-type. So we use this symbol N+, meaning that it's heavily doped N-type. So the inside of P-type semiconductor, if we introduce additional dopants, now we are running into the so-called compensation doping situation. But if the donor concentration over-dominates the the accepted doping concentration in the semiconductor bulk, then we can convert these surface regions into N-type semiconductor. And again, in this case, we are doping very, very heavily so that we can achieve ohmic contact with whatever metal we use to make the source and drain electrons. So we have ohmic contact for both source and drain. And then the spacing in between, we call this channel length. This is a channel. The channel, remember, is going to be on the surface of this p-type semiconductor. Remember, we have a strong inversion, as I mentioned earlier. It's a strong inversion situation. So for the bulk being p-type, then the surface will be n-type. We have electron channel. That's why we need to dope the two sides as n-type so that we can connect the two outside electrodes with the middle n channel. Okay, so there's also a minor difference between what we call a channel and what we use as substrate type. If we use a p-type substrate, then we are going to call this a n-channel transistor. The channel is the electrons. Okay, and then so in this case, we are basically under this so-called on condition. We apply an appropriate voltage bias on the gate such that we can induce a strong inversion at the surface of the semiconductor to connect the source and drain electrodes. Okay, so this is a strong inversion, and the channel that we produce on the p-type semiconductor will be a n channel. Okay, and this is on condition. And the off condition, it means that, okay, simply we don't have strong inversion. So as you see in the previous slide, we have many other situations to be not in the strong inversion situation. So in that case, we don't have a channel that's conductive enough to connect the source and drain electrode areas. So that means that even though you may apply a certain voltage across the source and drain, how much current you can flow through really also depends on what kind of gate bias we apply. That's the transistor action. The current, the source drain current depends on drain source drain voltage, and very critically, the gate bias that we apply. So this is a transistor action. All right, so now let's look at the so-called output characteristics of this MOSFET and see how we actually achieve this transistor action. So let's first look at relatively low drain voltage bias, drain source bias. So typically the source is grounded as well, same as the p-type substrate. So now in this case, we have a p-type semiconductor. So we have an n channel, and then we apply a voltage on the drain voltage. So in this case, as long as the voltage in between the source and drain electrode is not very high, we call low drain voltage, then basically you can treat this surface channel just like a certain resistor. So you have, or conductor, whatever you want to call it. There's some conductance, there's some resistance, okay? Finite conductance and finite resistance. So in that case, when the voltage you apply on the drain is not very big, then you are basically getting the ohmic behavior of this conducting channel. Okay, so in this case, in this case, the drain current will scale linearly with the drain source voltage. There's a linear dependence like what we have in the ohmic Ohm's law. But also understand that the conductance of this channel does depend on the gate bias. So there is a minimum voltage. Well, to induce, remember, to induce the N channel, you have to apply positive voltage. Okay, but there's a minimum voltage you have to apply to achieve the so-called strong inversion situation, and that minimum voltage we call a threshold voltage. So that's the voltage to just induce, just on the verge of strong inversion, just starting to have strong inversion. That's the voltage we need to apply. And that voltage will be used to create the band bending inside the semiconductor, but also remember you have electric field. So that electric field will cause a voltage drop across the oxide. Okay, so that threshold voltage has these two components. You have the band bending in the semiconductor so that the semiconductor has a different potential at the surface compared to the bulk. That's part of the voltage we need to apply. But at the same time, we have electric field running across the oxide that'll achieve, that'll result in some voltage drop as well. So that these are the two components for that threshold voltage to achieve the just on the verge of strong inversion for the semiconductor at the surface. Okay, so once you have some excess gate voltage, that excess gate voltage will be used to create that additional electrons inside this N channel. So the channel conductance will be proportional to the excess gate voltage you apply above the threshold voltage. So in this case, we call this a linear region of the transistor. That's when the drain source voltage is much smaller than this excess voltage we use to induce strong inversion. So in this case, this is the overall formula for the drain source current. There is the excess gate voltage we talked about. There's also current scales with the drain voltage. So there's the ohmic behavior. At the same time, the geometries of the transistor also matter. This L is length. Length is basically, think about electrons moving from source to drain. Well, actually, from drain, electrons moving this way. So actually, the voltage we apply on the drain voltage will be positive. And so the electrons moving this way, this L is distance the electrons need to move across. So we call this channel length. W is width. Remember, this is kind of like you have a sheet. So W is the dimension in the perpendicular direction. So this is W. This is the channel width. Okay. And then there's also the carrier mobility. Remember, if you have a certain amount of carrier, this voltage will determine the concentration of carriers at the surface. But if you want to achieve if you want to look at the current, you also need to think about the mobility of the carriers in this channel. So these are the electron mobility. And there's also this Cox. This is the capacitance of the oxide. Okay, remember the ability to attract electrons at the surface of semiconductor not only depends on the voltage. You can think about this as a capacitor. So the charge on either side of a capacitor, Q, is basically the capacitance times the voltage. So that's why this capacitance is in this equation. Okay, so overall, this, the important thing that you have here is that one, the current running across this channel scales with the voltage that you apply across this channel, the drain source voltage. That's why we call this linear region. There's a linear dependence. Then also this excess gate bias that we use to achieve the strong inversion, the capacitance, the ability for the charge to be attracted on either side of this capacitor, and carrier mobility, and the geometry of this transistor. All right, so now if you do apply even a somewhat higher drain voltage, then actually that voltage, remember, it's going to be, if you think about this channel, across this channel, you have 0 volts here, and then whatever voltage you apply on the drain. So there's going to be a gradual increase of the potential at the surface inside this channel just because that we apply a drain voltage. And if you do apply some if you do have some positive voltage here, that positive voltage may counteract against the gate voltage you apply. So maybe, let's say at this side, you have 0 volt potential for the channel on the semiconductor side. So you have all the gate bias will act to induce a electron channel. But as you move further away and closer to the drain voltage, then basically the voltage on the semiconductor side become more positive. Then it will reduce the excess gate voltage you have to induce electron channel. So essentially, what you see here is that the electron concentration will be gradually decreasing as you move further away from the source, closer to the drain electron. So that, as shown here. At some point, when you apply high enough drain voltage, it may be getting to a situation that this point may actually be no longer under the strong inverting situation. We call this a pinch off. Basically, the channel will be pinched, okay, pinched off at this point. And this, you can very simply thinking, if this drain voltage is equal to Vg minus Vt, that's the excess gate bias that you have on the metal side, well, that's how you balance it to get the semiconductor out of the strong inversion situation. So this we call a onset of saturation. We have pinch off in the channel. And if you apply, so this the saturation voltage for the drain voltage is very close to Vg minus Vt, the excess gate bias we have. If you apply even higher drain voltage, then you're basically moving the pinch off point further and further toward the source electron, okay? At this point, it doesn't mean that you cannot run the carriers through. Remember, even if you are not under strong inversion, you may be under weak inversion. So you still can flow the electrons through. It's just that the conductance becomes a lot lower because the electron concentration is lower in the weak inversion situation. So in this case, this channel region is going to have high conductance, but this region, the pinch off the region, will have lower conductance. So essentially, all the voltage drop is going to be used to pull the carriers through this low conductance region. And as a result, overall, the current will not further increase as you increase the drain voltage. The excess drain voltage you apply only actually is used to push the pinch off point further toward the source, and then you're pulling the carriers through this low conductance region. That's what this excess drain voltage is doing. So that's why we have this saturation region. So overall, by the way, in the saturation region, as I mentioned, this drain current no longer depends on the drain voltage, but it does still depend on the excess gate voltage we apply, and actually it goes by the square of the excess gate voltage. You still have the mobility of the carriers, and then also have the oxide capacitance in the equation, and the geometry factors of the transistor. So just to sum it up, you have this ideal MOSFET output characteristics. The output characteristics is plotted basically the current through the drain source electrode, the drain current, plotted as a function of the drain voltage, and at multiple given gate bias. Okay, gate bias 1 volt and 9 volt in this case, and the highest one is the 10 volt. So those are the gate bias, and then so you can identify a few regions where one is at low drain voltage region, you have the linear dependence. This is the ohmic region of these channels, so you have the linear dependence, we call it linear region. And at very high drain bias, you run into this saturation region when the current no longer depends on the drain voltage. Obviously, you see that it depends on the gate bias significantly. Okay, so these are the two regions. In the middle, you have this nonlinear region, which is sort of transition going from the linear to the saturation. So we have these two equations for the linear region and for the saturation region, and understand here that we also apply a correction of VV in the equation. This is going to be small just because that the drain voltage is going to be much smaller than VG minus VT anyways. But to be accurate, there is a correction factor here. And so here you see that this drain voltage in general is a function of both the drain bias and the gate bias. Okay, so you can take some conductance, and if you want to look at the channel conductance, basically you take the derivative of the drain voltage versus the drain drain current versus the drain voltage. Okay, that gets you the conductance and at any given constant gate bias. You can also look at so-called transconductance, and this is what really makes this a transistor. Okay, transconductance. So basically, at any fixed voltage for the drain bias, then let's look at how the current can be influenced by the gate bias we apply. For example, if you look at, let's say, at 16 volt for the drain bias, now you can plot the drain current as a function of the gate bias, and then you see how much the gate bias can influence the drain current. It's very, very dramatic increase. So as you go to higher and higher gate bias, you can really make the channel current, the drain source current, very, very high. Okay, but at the same time, you can also suppress it if you apply a gate bias less than the transistor threshold voltage. And if you do follow these two equations, you can get to the channel and transconductance in both the linear region and saturation region. And for example, if you look at in the linear region, the channel conductance, if you plot the channel conductance as a function of gate bias, well, you're going to get a straight line. Okay, there's a linear dependence between them. And then when you look at the intercept of this line, so you plot GD, the channel conductance, as a function of VG, you get a straight line, and the intercept will be VT. That's how you can determine the threshold voltage of this transistor. And the slope is given by this product. So if you know the geometry of your transistor and you know the capacitance of the oxide, you can really determine the mobility. So this is one way to determine the carrier mobility in these semiconductors. But understand that this is so-called field effect mobility. So mobility is really looking at the carriers at the surface. You have a inverted channel at the surface of the semiconductor, and then you look at the carrier mobility. So this field effect mobility may not necessarily be the same as the carrier mobility in the bulk, just because the surface could have very different electronic characteristics compared to the bulk. Okay, it really depends on what kind of surface you have. And the good thing for the silicon-based transistor is that the interface between silicon and silicon oxide can be managed pretty well. And we have a lot of understanding on how to make a more or less defect-free interface between silicon and silicon dioxide. There are a lot of mature ways of making a high-quality silicon dioxide on a silicon crystal. And so in most cases, the field effect mobility of these transistors, silicon-based transistors, will be pretty good. But for some even newer materials, you may not have that kind of ability to make a high-quality insulator on the surface, and that may make this field effect mobility to be significantly different. So it's really a surface property of a semiconductor, and depends on how you manage that interface as well. All right, so I guess without questions, we are running this lecture very quickly through. So in terms of student learning outcomes for PN junctions, it's important that on top of what we have talked about under thermal equilibrium in the last lecture, on the bias situations, you need to be able to identify the polarity of the voltage bias. How does the bias change band bending, depletion region width, and what kind of carrier concentration profile you're going to have, and more importantly, how does the current actually flow? So quantitatively or qualitatively, you need to understand the rectifying behavior of the junction on the different forward and reverse biases. And then we have this Shockley diode, ideal diode equation, which will allow you to actually calculate the currents on the forward and reverse bias. For the metal oxide semiconductor structure, the MOS structure, qualitatively, you should be able to understand how the voltage bias on the metal electrode can influence the band bending in the semiconductor, and then also quantitatively, can you predict what kind of condition, what kind of bias, what kind of surface potential you have in order to achieve strong inversion in the semiconductor? The strong inversion is the necessary condition to use this MOSFET, because we are operating this channel will to create a conducting channel on the surface. We have to have this strong inversion situation. Okay, and so for the MOSFET, you should be able to quantitatively describe how it operates and why we have this linear region, why we have saturation region for this output characteristics. So with that, I'll end this lecture. And before we get to the next lecture on Tuesday, understand that we do have a quiz coming up the following Thursday, which will cover both the metal semiconductor contact, pin junction that we talked about in the last two lectures, and also what we talked about here today on pin junctions on the bias and MOSFET. I also upload a homework set for these three lectures, and then we'll also talk about how we are going to handle the grading situation in exam 2, especially on the calculator issue. All right, if you have any questions, again, feel free to reach out to me through email, or you can request a Zoom conference with me if you want to have some special time to talk about specific issues or concerns you may have. Okay, see you guys on Tuesday.